Okay, good day, everyone. Let me welcome to the BES seminar. So let me first introduce today's speaker. So today we're very happy to have Professor Frank Geurts from Rice University. He has been leading the experiments of the relativist heavy ion group at the Rice University in Houston since 2008. So Frank received his PhD from Utrecht University in Netherlands. And since then, he worked as at the Philips Research Laboratories in Netherlands, Rice University in Houston, and also at CERN. So at the Philips Research, he worked in the digital design group, where he has been involved in various of heavy ion experiments, ranging from fixed target CERN SPS WA93 and WA98 experiments to STAR experiments at the relativist heavy ion collider at Brookhaven, and also CMS experiments at the Large Hadron Colliders. So Frank has been the light flavor spectra physics working group conveners, physics analysis coordinators, and also deputy spokesperson for the STAR collaborations. In addition, he is involved in the CMS collaborations, where he is leading the online software group of the NCAP muon detector systems. So without further ado, I will leave the screen to Frank. Frank, you can start your presentations. So just before the talk, just a reminder that if you have any questions, please type them in the chat. And if it's a short questions, I will remind Frank to solve it on the fly. For longer questions, we'll leave it to the discussion sessions. So Frank, the screen is yours.
Thank you, and thank you for the introduction. So hope you can now, I think you can see my starting slide. Okay, thanks. So thanks for inviting me to talk on this particular subject that's dear to my heart, and dileptons and somewhat closer to the beam energy scan physics. What I'll be discussing with you all today is kind of in this outline put to this slide, which is I'll briefly discuss a little bit about the phase diagram, QCD phase diagram, what role dileptons can play in exploring this phase diagram, bring some theoretical considerations to the table, followed by some experimental considerations, and then actually hope to convince you that dileptons really provide us with a multi-tool that allows to dissect and measure in various ways the physics of the QCD phase diagram, and then briefly discuss some future prospects. So the QCD phase diagram, there are many ways in which you have seen in the many years the depictions of the phase diagram, starting with what Cabibbo and Parisi put down in their paper almost 50 years ago, which is very basic, but certainly something that started a field that by these days has become much more refined as a more recent plot. Picture that I show you, let me get this a bit out of the way. So that I show you on the right side with some input from Lattice QCD, and then some more colorful pictures, as I show below, where you can see experiments jotted in and motivations for example, a beam energy scan that took place at RIC. What's clear is that experimentally, and this comes back again to say, for example, the RIC beam energy scan. Experimentally, you can access these different regions of the phase diagram by varying the center of mass energy of your collisions. And over the years, we now have seen experimental data that's been collected that there's about 3 to 4 orders of magnitude in this square root of S. We see that LHC and RIC provide access to the low mu B region. Actually, I see that I should not really say low. But fair cis 18 are allowing us to kind of start to reach into higher chemical potential region. We see that whether you look at high energies at LHC or RIC, you will be probing more this crossover region, while going to the beam energy scan that RIC and FAIR and other facilities that are coming up that I discuss later allow you to really probe that higher mu-B region. Experiments at AGS, SBS, like I said, CIS and the RIC beam energy scan, they really allow you to probe these high mu-B regions that you can, on the one hand, look for crossover, but also look for effects of, say, first order phase transition and this conjectured critical point. What particular role, sorry, I jumped in my slides for some reason here. So one of the major goals is then to chart this QCD phase diagram. And here on the right side, you see again this phase diagram, but this time more experimental facilities painted in it. Charting this QCD phase diagram really means that we're looking for example, turnoff of particular QGP signatures that we established at higher energies. Look for effects in suppression, nuclear suppression, elliptic flow, and see what kind of phase transition this is. Is this a first order phase transition? Can we see the changes in the equation of state? And would that be something that we can see in, for example, the mean transverse mass of identified particles, or otherwise in non-monotonic behavior of the directed flow at mid-rapidity? And then with a crossover region at low mu-B, and what is a phase and what is a what possibly is a first order phase transition at higher mu-B, the question about a critical point comes up where one of its signatures would be the divergence of correlation lengths, which would be something we can measure in higher moments of conserved quantities. And I list here a few of those. So the question is, what can dileptons play here? And I'll discuss that next, and I'll bring up some further theoretical considerations following. Dileptons in this are really very good penetrating probes, and that is because they are colorless objects. They have no interactions with strongly interacting matter. And so throughout the evolution of a collision, you can see them produced in various ways at the early stages of a collision. Then when the fireball develops, we see electron or electromagnetic probes being emitted, and at later stages of freeze out, we see that as well. Dileptons, or leptons in general, have long mean-free paths. That means that they not only that they actually make it all the way to our detectors, and we can do direct observations of these dileptons. And I think one of the most appealing parts of the dileptons is that it gives us this additional knob in measuring spectra, and that is to look at the invariant mass in addition to momentum. So as I said, the contributions to this invariant mass spectrum of dileptons come from a whole variety of sources that include primordial emissions, say pre-equilibrium, where you have Drell-Yan type of interactions that result in quark, anti-quark annihilation that we'll see in dileptons. We set the stage for other contributions to dileptons through the heavy flavor production that happens in this early pre-equilibrium phase. And then as the system further progresses, we'll see that thermal radiation from a quark-gluon plasma or from hadronic matter, again, is an important source of dilepton radiation, whether that is from quark anti-quark annihilation or from the pion channel. We see that in this hot hadronic medium, the in-medium rho is becoming important important particle to deal with. And that includes not only the rho, but other kind of 4-pi processes. And that was something we'll discuss later on, including, say, the rho A1 mixing. And then as the system further expands, we'll have to deal with many of these long-lived hadron and resonance decays, which result in a whole slew of decays from light mesons, pi zeros, etas, omegas, phis, and that includes not only the regular decays, but also the Dahlitz decays. And here we are becoming sensitive to the in-medium modification of particular factor mesons. And then, as I said earlier, the stage was already set by a lot of the heavy flavor production. We'll be seeing decays of quarkonia, J psi, and correlated DD bar pairs that in itself may also be affected again from nuclear modification effects. If I take these particular sources of contribution and I kind of look here in the right at where they dominate this invariant mass spectrum, it's actually interesting to see that going from, say, a high mass range to a low mass range, we see something of a time ordering, at least in terms of what is the most dominant source. If you look at high invariant masses, you'll see that there the predominant, what really the dominant source is the primordial emission, where Dralion actually is the most dominating source, where you can see the heavy quarkonia, J psi and psi prime. I mean, I put here upsilon, that's obviously a little bit off charts here, but this is really where we see the early sources reflected. And as you move to lower masses, you can see in this what we refer to as this intermediate mass range, which basically is between, say, the J psi and the phi meson. This is a region in which we have more access to thermal radiation from a quark-gluon plasma, but still, this is also where we can see the effects of the semi-leptonic decay of correlated charm. And again, that might be something that indeed in the heavy ion environment is also suffering from modification, nuclear modification. And then going to really low mass ranges, this is where you'll see the most contributions coming from these factor meson decays. And that includes modifications of factor meson decays that you'll be sensitive to. It's also a range where you can start to look at fireball lifetime measurements. And as we'll discuss later on, here you have some opportunities to look at transport coefficients, specifically with respect to electric conductivity. So let's talk a little bit more about some theoretical considerations. In the calculation of electromagnetic production rates, you use from thermal field theory a current correlation function, which looks like this equation that I show here above. And the current operator here, G mu, basically is this well-known combination of all the quark flavors here. And if I just go up to the lightest quarks, it takes on a form that you may well recognize. And this current correlation function is what we can use to express the thermal emission rates for photons. Okay, sorry, I thought I heard it. So for thermal emission rates for photons as follows, and for dileptons. And you can see that they really are both governed by the same underlying spectral functions. That's to say, in the dilepton case, you'll see that there's a lepton space factor, but for invariant masses that are significant or much larger than the mass of the lepton, this space factor is practically 1. And you'll see that we, in addition, have this thermal Bose distribution that is part of both the thermal emission rate distributions. So like I said, they're both governed by the same underlying spectral functions, albeit with somewhat different kinematic regimes. Now, in connection with the vector mesons, if you look on the right side, you recall this well-known distribution of the ratio of dileptons to hadrons divided by, or electrons to hadrons divided by the E plus E minus to mu plus V minus distribution. And you'll see here that above, let's say, 1.5 GeV, this is a very smooth distribution. But below 1.5 GeV, you'll see here the effects of contributions of many mesons. And so taking another look again at that J mu that I showed earlier, where just up to the lightest quarks, we can write it as follows in terms of the up, down, and strange quark. You can go a step further. You can group that into these isospins that allow you to identify the rho and the omega and phi. And if you do that, this J mu will take on a form like this, where you have a explicit J mu that you associate with the rho meson, the omega, and the phi meson. And at low mass, low invariant mass, in other words, in this region here below 1.1 GeV, you can write this correlator, or the imaginary part of the correlator, which is what's going into your production rates, in terms of these contributions, these propagators that see contributions from the rho, the omega, and the phi. And you can see here already by just looking at these numerical values that that the rho here on the right side. And so this vector meson dominance that we see below 1.5, 1.1 GeV, you see here that they carry the same quantum numbers as the photons. They directly decay into photons, as is depicted here in this little Feynman diagram. And again, that the rho is the dominant source, which actually is even more dominant given the much larger decay width that the rho has compared to the omega and the phi mesons. Focusing a little bit more on the rho meson. So this rho meson will interact with the hadrons in the medium. And if you look at the propagator of the rho meson, you'll see that there are various contributions to its self-energy. There is the contribution that comes from its interactions with the pions, there's the in-medium pion cloud, and there is interactions that relate to the interactions of the rho with either the mesons or with baryons. And it's important to realize, which I show here with these two plots on the right side, that the broadening of a rho meson really, the baryons are playing an important role in this. So on the right side here, you can see the modification of the rho meson, where you do not take baryon interactions into place. And yes, you can see that it is modifying, but it is not showing this clear broadening that we'll talk about more if baryons are not included. So baryons really are an important aspect in the broadening of the rho spectral function. Another thing I want to bring to your attention is that as you know, the QCD Lagrangian contains a subgroup that is chirally symmetric. So that chiral symmetry is there in the limit of vanishing quark masses. We know from lattice QCD calculations that, as you can see on the right side, that actually we see that there is a dynamical formation of a quark anti-quark condensate. And as a result of this dynamical formation, we see that chiral symmetry is broken in normal nuclear matter at low temperatures. And that has a profound effect on the chiral partners and results in this significant mass splitting between the chiral partners, which is, as Weinberg said, square root of 2 in the mass between the vector and the axial vector. Well, it's a little bit more than a square root of 2, but you see here that indeed the result of this breaking of the chiral partners is resulting in about a 500 MeV between the for the rho and the A1. And similarly, the nucleon, for completeness, the sigma and the pi, these kind of mass splittings are the result of the chiral symmetry breaking. Weinberg's or chiral sum rules allow us to connect the spectral functions that we discussed earlier to these condensates, where the difference between the vector and the axial vector can be expressed in terms of this pion decay constant, which can be related to the quark anti-quark condensate. And you see here on the right side, indeed, a depiction of this rate versus square root of S, and you can see here, or square root of S, versus the mass squared, and you can see here the rho, the vector, and the A1, in this case, the axial vector component. The restoration, on the other hand, of this chiral symmetry will manifest itself then in the mixing of these V and A correlators, and the rho meson is expected then to melt in a hot matter, while the A1, as you can see from this calculation on the right side, is not only decreasing, but it also starts to degenerate. You can see here as a function of temperature in this calculation that was done by Paul Holler and Ralph Rep in a hot pion gas. You can see indeed how the axial vector component, the A1 in this case, as the temperature goes up, is slowly degenerating and decreasing in its mass. And you see increasing the effects of this mixing. I should point out, and you probably already saw this, that this is done in a hot pion gas. So you can see here that in this particular calculation, the baryons are not particularly participating, because you actually see that the pion the rho meson is not showing this broadening as we discussed earlier, but it is very illustrative of how indeed we see the A1 decreasing and degenerating, exactly what you would expect from chiral symmetry restoration. And on the left side, you can see this for the A1 and the rho again, where you can see these two masses as a function of temperature slowly move towards each other, or rather the A1 move to the mass of the rho. In terms of the mass spectrum, this rho A1 mixing is something you would expect if you look in again at the invariant mass distribution. You would see in this particular calculation, which involves a full chiral mixing, you see indeed that the vacuum, that this area right below the phi meson will start to fill up as this A1 component starts to move into, starts to generate and drop its mass towards the rho meson. And this is one potential signature of seeing a full chiral symmetry, or full, in this case it's a full, of seeing a chiral symmetry restoration. So this mixing in the words of Ralph Rapp, moves the strength from this axial vector here into the vector channel. Okay. So with that, just some brief experimental considerations that I have to bring up, because we'll be talking a little bit more about experimental results next. The biggest challenge or the biggest experimental challenge that we're facing is the fact that dileptons, because you do well, you're looking at two electrons, you need a large acceptance and you need a high purity PID. And on top of that, you also want to have good momentum resolution. Electron PID typically is something that we achieve by a combination of a tracker with either a time of flight measurement and energy loss measurements, or using a tracker with a rich detector, where this rich detector then will have a very high Lorentz factor thresholds, so that you will effectively suppress as much as you can hadrons in your rich signal. Muon PID is mostly about trying to get rid of all the hadrons that come along with it. So you can see here as for example, Na60 plus proposal, or which looks a lot, of course, like Na60, you have a significant hadron absorb that you like to put in to suppress all hadrons so that you can then identify the muons after the absorber. But you also want to make sure that you do proper tracking before and after the absorber. As wonderful as dileptons are in terms of that they don't interact much with strongly interacting matter, etc., they also are rare probes. And so we have to face the fact that the production rates are very low. And to give an example, every time we're talking about detecting a row through a dilepton channel, we have to realize that that is a significant lower yield than if you would detect a row through a pion channel. As if that wasn't enough, you will face large combinatorial backgrounds in the reconstruction of dileptons, in part because there's detector materials that lead to photon conversions, which you will see as dileptons in your detector. We have, as you saw in one of my earlier plots, you have a lot of light mesons with Dalitz decays that add up quite substantially. And then if you're looking at muons, you also have to deal with the fact that there are, well, not really fake, but fake muons. In other words, muons that are not coming directly from the collision, but rather are the result of weak decays. And you have to be able to handle those as well. And as a result, your signal to background ratio can be much lower than 1% if you look at large multiplicities. And that also means that you really need to take a lot of care, as I try to show here, in understanding your background very precisely. Because with these signal to background ratios that are that low, it means that if you are trying to extract a signal, your signal to background ratio basically multiplies any uncertainties in your measurement. So you need to be very careful in understanding your backgrounds, whether they are combinatorial backgrounds or other. Well, with that, let's dig into it and look at this multi-tool that the dileptons provide us with. And what I first want to look at is just mass, a very mass spectrum. Let's look at the dilepton multi-tool as a spectrum. From a spectrum, a significant enhancement in this low mass range came from the Cirrus experiment that looked at E plus E minus. And what you see here is that this significant enhancement that they saw is not something that they can explain by just assuming, and it's in light green, unfortunately, here, that they could account for through a vacuum row meson. So while all the other contributions, cocktail contributions, if you want, to the spectrum seem to be able to handle this very well, the row meson, the vacuum row, was unable to describe the low mass range enhancement that was observed. There were two candidates to help explain how this row was modified. One was in actually a decrease of the row mass, this brown row model, which the expectation was that the mass of the row would just scale with the QQ bar condensate. And the other one was what I already showed on earlier, this broadening of a row spectral function. And if you look at this on the right side here, you can see actually that the dropping model, which is this dashed dotted line that goes along here, and the row brown, the dropping model is the dashed dot, yeah, and then the solid line, which is the row broadening. Both of them were, with the statistics at hand, both models actually showed a good agreement, both at 158 GeV and at the 40 GeV. So while it was clear from the Cirrus experiment that there was an enhancement that could not be explained from assuming a vacuum row, the two approaches, the two views on whether this is coming from a decrease of the row mass or from a broadening of its row spectral function, there was not a conclusive, there was not yet a conclusive statement based on the statistics at that time. Enter the Na60 experiment, which instead of dielectrons uses dimuons, and you can see here very clearly that in this low mass range, the vacuum row, again, is unable to explain the distribution that was observed by Na60, but also that the dropping mass model, which is this green dashed line, was unable to explain the data that was seen. Instead, Rapp and Wambach's broadening very nicely described the data. And thus ruled out this mass dropping scenario. At Rick energies, both the STAR and the Phoenix experiment looked at dielectron spectra as well in the low mass range. And again, they both also came to the same conclusion that the data is not supportive of a vacuum row. You see here on the left side a plot where you can see indeed that the vacuum row is not described by the data at all. And a couple of models that involve a broadening of the row, on the other hand, seem to be able to describe the data minus the cocktail being, again, the contribution of all other vector mesons, seem to be describing the low mass range very well. And the same was a conclusion that came from measurements that were done at the Phoenix detector. So with the uncertainties, there was an agreement here between experiment and theory. With Na60 and Cirrus at SPS energies and top Rick energies, their axis was clearly established. And the question was then, how can we take another look at these in medium modification and study whether there are these indications of chiral symmetry restoration? And the Rick beam energy scan was indeed set up such that we would do an exploration in the low mass range from top Rick energies down to these SPS energies and set up an excitation function where we would study systematically the dependence on temperature, the total baryon density, and medium lifetime as you lower the square root of S, the initial conditions of your collision. Now, for example, in this left plot, you can see that if I take, say, the proton plus antiproton divided by the pion, this ratio as a proxy for the baryon density, you see that actually from top Rick energies down to mid beam energy scan energies of about 20 GeV, this is not changing much. This is fairly constant. And this is the total baryon density, not the net baryon density. And indeed, we saw from beam energy scan phase 1 here that this normalized axis yield that is shown here in this right plot is not showing any, or not showing a significant dependence on the square root of S. And as I said, neither does the total baryon density. But as you look at these plots, you also, it's clear that the precision from beam energy scan 1 is somewhat limited to really go a step further and constrain model assumptions. There are model assumptions put in this plot as well from RAP, Andrus, and PHCSD models. And you can see that the uncertainties are still fairly large to be very conclusive on distinguishing the various models. And that especially holds for beam energy scan phase 1, was holding for energies below 19 GeV, which is why in beam energy scan phase 2, a lot of the statistics requirements has been significantly increased to now further study this region from, say, 19 GeV down to 7.7 GeV, and maybe even drop to as low as 3 GeV. So that will allow us to actually investigate how, with a total baryon density going up as you go to lower and lower square root of S, how this normalized yield is following. Okay, let me move on to the to another aspect of this multi-tool Dilepton device, which is to use it as a measure for the fireball lifetime. I think it was in a Quark Matter conference in 1990. This was a topic that was discussed, and there's this paper by one of the papers here is by Uli Heinz and Lee, where they also discuss already in 1991 using this rho peak as a clock for fireball lifetimes. And NA60 introduced this rho clock and showed that the centrality dependence, that there exists a centrality dependence, as you can see on the right side here, of the axis yield as a function of, well, centrality or the number of charged particles per atom. And you see that this yield ratio can go up to 6. So you can see that you can reach up to 6 generations compared to what a vacuum row would look like if you focus on the axis in this range just below the vacuum row and omega peak. It was observed that these normalized axis yields, if you look at this in this plot here, they seem to be tracking very well the medium lifetime. So in this plot here, you can see 2 vertical axes. One is the fireball lifetime, which is a combination of the hadronic and the QGP source. But you can see here how that tracks, and how indeed you can see the NA60 centrality here have something similar. So with that observation that these axis yields really follow the medium lifetime, could this be something that allows us to have a device that is sensitive to, say, first order phase transitions, where you may expect some plateauing in this square root of S plot, or if you get close to a critical point in doing such a scan, be sensitive to correlation lengths that are increasing close to a critical point, and that will therefore have an effect on the lifetime of the system. Would you be able to see this in actually the row clock in measuring the lifetime through the dileptons in the low mass range? So again, to remind you, we'll see that there are several measurements done, in specifically looking at the range below the rho and the omega mass. And if you look at these results from Hades and A60 and STAR, they look promising. But on the other hand, the experimental uncertainties are pretty large, and so you cannot really, from a plot like what I show you here on the right side, see any effects that would point at plateauing. And obviously, there is not enough data just here yet to say anything about anomalous increases in these yields. On the left plot, you see again also something that basically takes this calculation from Rapp and Van Hees, and we put some of the data from STAR and Na60 for different centralities or number of charged particles in this. And you can see indeed this tracking, but it also should be said that, again, the uncertainties are large. And to do this, you really need high statistics measurements. All right, let's move on. Another thing we can do is we can look at using the dileptons as a thermometer. And I have to remind you that thermal dilepton radiation, in the low mass range, you have these dilepton spectra that are very much dominated by the light factor mesons. And in the intermediate mass range, you have an axis to this quark-anti-quark continuum. The dilepton rates in this intermediate mass range can be expressed as follows. And using the mass, invariant mass, which is, as the word says, invariant, you actually, by construction, have a measure that is independent of any blue shifts effect of flow. But since we are looking at an evolving system, you are still have to be aware of the fact that any temperature measurement you do there is one that is an average over the full system evolution. Now, other bulk temperature measurements exist, and they typically rely on hadron yields and spectra, which you measure after the chemical freeze out or after the kinetic freeze out. And we know here already some trends where, for example, the chemical and the kinetic freeze out temperatures change as a function of square root of S, or rather, I should say, where the kinetic freeze out temperature starts to drop and the separation between the two increases as you go to larger kinetic energy. Using the dileptons, on the other hand, would allow you to probe really inside these particular freeze out, before these freeze outs happen. So at SPS and RIC energies, we see that in the low mass range, because I first want to kind of focus on the low mass range temperatures here, this is really a predominantly thermal dileptons that come from the medium rho. If you take that into account by including, in addition to this rate that I showed here, a Bright-Wigner in your fit, then recent STAR results that were taking advantage of high statistics 27 and 54 GeV actually show that compared to, say, Na60, we can extract more or less same temperatures out of this range, which are all around, say, about 170 MeV. So these temperatures are not only show a similarity in what we see at Na60, which in this plot here, we show the Na60, the 27 and the 54 GeV data. in one plot, you see that these the temperatures are more or less the same. But you also see that these temperatures are pretty close to the chemical and pseudocritical temperatures. And that is an indication of the fact that we are really looking here at rho mesons that are emitted from a hadronic phase, and that this is predominantly around the phase transition. And so this is an interesting observation in the temperature extraction using dileptons in the low mass range. At higher μb, we've seen a few years ago that Hades was able to provide a very nice measurement of the low mass range, higher density, really, this is much higher. And you can see that the medium rho is substantially modified. There's hardly any structure visible in their mass spectra. If you look careful in their recent silver system, you can see something of a structure. But here they're gold, there's hardly any structure visible. So it's almost structureless exponential distribution. And Hades in their Nature paper and in their recent preliminary work on silver showed that the low mass range temperatures was between 70 and 80, where is it there? 78 MeV. That's clearly below the critical, pseudocritical temperatures. And if you take this plot that I showed earlier, there you can see where indeed the Hades point sits here. Going to the intermediate mass range, this will give us the access to the quark anti-quark radiation. And Na60 was really the first one here to provide us with a dimuon measurement that yielded a value of 205 MeV temperature in the intermediate mass range. Recent star results using E plus E minus showed in 27 and 54 GeV a temperature of about 320 MeV, which seems rather high, but one should be careful also here in that the range in which the fits were done in star is from 1.2 to 2.5, and if we would compare this with Na60 in that same range, we actually see that the temperature indeed is somewhat higher, and we see something in the order of 246 MeV. Now, nonetheless, this average temperature is higher, and this could be due to just a longer lifetime. The system has lived longer, has been radiating longer, and we can actually see that as a reason why we see higher temperature, which is actually furthermore supported by the fact that not only do we see a longer system, and so we were able to see these higher temperatures, but you also see that the yields are in between, say, the Na60 and the star data. The yields are somewhat higher, so that is furthermore supported by that observation. It's clear that the average intermediate mass range is well above the pseudocritical temperature. And I show here on the right side now, in addition to the low mass range plots, low mass range temperatures of star and Hades, now these intermediate mass range temperatures that are well above the pseudocritical temperature and are probing really into the Platonic regime. All right, let me move on to a few of time. Let me hurry up a little bit. So let me move on to a few other interesting aspects you can do with this dilepton multi-tool, which is which I kind of refer to as the barometer, polarimeter, and multimeter thing. So dileptons as a barometer, well, looking at MT distribution, so not so much using the mass scale, which I just, if you do temperature as a function of the invariant mass, this is by design a Lorentz invariant measurement. If you would take a particular mass bin and then look at the momentum distribution of dileptons or the MT distribution of dileptons in this, you are more sensitive to collective effects to flow. And so we'll see that, in fact, this is this plot from NA60, where as a function of the invariant mass, this effective slope, this T effect, the effective temperature, you can see in the range which is dominated by mesons, you can see that that slope linearly rises, peaks at the rho, which again dominates the spectrum, and then sees a sudden drop in the intermediate mass range, where it hardly changes as a function of mass, not as dramatic as the linear increase that you saw in a low mass range. And so in the low mass range, it's clear that this linear rise is the effect of a radial flow component that pushes the radiation and leads to this particular effect. And again, right, be careful to interpret this as a real temperature, because it is a temperature that is, as a result, severely blue shifted. As I said, in the intermediate mass range, there's no such evidence of a mass dependence, at least not within the uncertainties that are shown here. But you do see that the temperature here, that this effective temperature, is something in the order of 200 MeV, which again is agrees with the dominant source in this platonic matter to be not that different from what we saw already in the measurements, earlier of the temperature, that this 200 MeV is a little bit below the 205 or the 250 MeV that we established by doing a temperature measurement on the intermediate mass range mass distribution. Okay, what else can we do in dileptons as a barometer? Well, you can study the azimuthal anisotropy, and this is quite a challenging analysis, where you want to isolate the V2 of the excess dileptons. And in this paper by Chatterjee and her collaborators, you can see that you can distinguish the hadron gas and the QGP. But in order to do that, you really need to get your uncertainties down to 4%. But you can see indeed that the total momentum integrated V2 has very clear characteristics that would allow you to look for this azimuthal anisotropy. Star a while ago has done this, and while it was within the statistics of about 800 million events, it could indeed extract the V2 from the pi0 Dallas decays. Again, that's not the excess dileptons that we're seeking for. But from a proof of principle, it was shown that at least the V2 from the Dallas decays of the pions was consistent with published pions. So you have a tool that looks promising, but you do need a lot of statistics, as is also shown in this summary plot from the star analysis of a inclusive E plus E minus. Again, this is not looking at the excess, but the exclusive. You need a lot of statistics, and this is with future detectors becoming much more accessible. Another thing that one can do is to really look at the angular distribution of the dilepton rates. And you can express this angular distribution of the dilepton rates in terms of a set of angular distributions that have these anisotropy coefficients. they give us some information on what the original polarization of the virtual photon was. You can relate that to production mechanisms. For example, you can show that for a transverse polarization, for Brian, this should be +1, and that for a longitudinal polarization, typically in pi annulation, this should be -1. And you can see here on the right side the calculation where integrated over mass Qt and Y, these coefficients are small, very small, less than 1%, but finite polarizations, as you can see in this particular plot here. NA60 has made some attempts to look at this polarization. Their measurements are consistent with null findings, but then again, they also have large uncertainties. It is important, though, to realize that that you clearly need high statistics measurements to be able to look for this non-zero polarization in a thermal system. And you need to really be also very clear that you understand all these relevant processes that contribute. For example, a measurement done by Hades was seeing a significant non-zero polarization, but this was so it was expected that this was more coming from contributions that came from the delta resonances. Okay, last but not least is to use dileptons as a multimeter, or to determine electrical conductivity. The electrical conductivity is defined as this E mu in terms of the electrical field, and there's this electrical conductivity sigma EL that stands that relates the two. And what's interesting is that this electrical conductivity can be extracted from the same EM correlator that we discussed early on, which means that there is a way to look at this in the rates that we measure of dileptons. Specifically, if we go to very low masses, we should be able to say to do a measurement of this electrical conductivity. And there's a wide range, as you see on the right side, quite a wide range of theoretical predictions that that if we have access to this low mass range, we could actually really put in some experimental constraints to this range, which again, this is a logarithmic scale, so there's certainly an experimental challenge to provide measurements here. And an experimental challenge it is, because it requires that you need to really push your measurements into this low invariant mass and low PT. And on top of that, not only do you need to push into these little carved out quarter circles that you see in the mass versus momentum plots, or mass, from say star and Hades and the expectations for Alice's ITS3 tracker. You need to push really into this range so that you can get as low in mass and momentum as possible. But you also need to understand really very well your references. In other words, you need to understand all the cross sections of the hadrons that you will need to subtract in order to get a proper measurement. Okay, let me start to wrap up and go from these various aspects that the dileptons can provide to some of the future prospects. And what I show you here is on the right side, the blackboard that we were putting there in kind of mapping out at an ECT workshop about 8 years ago, where the perspectives on photons and dileptons. And you can see, for one thing, you can see that we were pretty well in describing when the EIC was going to come in the picture. But you see that there's a whole set of set of detectors that at various times we expect to come online to participate and give us these high statistics measurements. Because that's the thing, for future measurements, it is really relevant that, as you've seen from several of the experimental data that I showed thus far, that uncertainties are large. And so we really need high statistics, which not only means that we need to look at very high interaction rates, but also make sure that we have large acceptances. It is equally important that while you can have very high statistics, if your references, the cocktails, the mesons or the heavy flavor or Dralion contributions that you'd like to subtract, if those still come with substantial uncertainties, then that's not going to help your high statistics much. So you really also need to make sure that your references are precise, which implies then that your detectors should have the means to indeed provide some part of that. So you need to look at multi-purpose detectors to improve or guarantee a good reference. And then you want to really hammer down on your backgrounds. So as for example, the tracker for LS3, you want to really make materials as contributions from materials as small as possible, because materials lead to conversions, and conversions lead to E plus, E minus that will add up substantially into your invariant mass spectrum. And of course, you want to do very precise PID of the electrons and muons. Now, if you look at this diagram that I lifted out of the letter of intent for NA60 plus, you'll see indeed a whole slew of detectors, new detectors that are proposed, especially, and what they all have in common is that they are really looking at high interaction rates as a function of square root of S. You have LS3 sitting here at the high energies, but in the low square root of S or high mu B, you see several detectors, NA60, CBM, DHS at JPark, CEE, and BMON and NPD at NICA, that are proposed to really, and include Dilepton and dimuon programs at really substantially higher interaction rates, and all have in common to be more general purpose detectors, so we can indeed make sure that our references are well under control. So let me summarize, because I'm already past the hour. I think that Dilepton measurements, I hope I convinced you that Dilepton measurements really provide access to a particularly wide range of unique physical observables. I discussed several of them here today with you. There's the potential of accurate Dilepton measurements that is well demonstrated at experiments that took place at SPS, at FAIR, at RIC, and at LHC. And at the same time, we've seen some very interesting new theoretical developments and insights that allow us to look again at these data sets and extract other informations. A future experimental progress, high statistics is key. And we see that there is certainly an increasing worldwide effort to further explore this QCD phase map using dileptons and deliver its landmarks. And with that, I thank you for your attention and conclude my talk. Thank you.
Okay, thanks, Frank, for this clear and well-structured talk. And now we are going to the discussion session. So I haven't seen any question on the chat yet. So if you have a questions, you can either put on the chat or you can also raise your hand and ask the questions. So maybe I can start questions that I have. So in your beginning of your talk, you mentioned about the row A1 mixing, about probing the color restorations and possible signatures that can be attributed to that in the dilepton spectra. How far are we from actually measuring these in experiments? How large is the sensitivity do we have?
Yeah. Let me pick the plot that I think is all right. So in order to measure this, we should be looking at this. I mean, so one of the ways to look at this is look at this range just above the phi meson, and at this point, if you look at the uncertainties that current experiments have, it is very difficult to see this vacuum distribution fill up because of the row A1 mixing. However, in the proposals that come from, say, NA60 plus and the LS3, this is exactly the area where they want to focus at measuring the effects of this row A1 mixing.
Okay, thanks. Let's Bert, you have a hand first.
Yes, Frank. Thank you for this very broad overview. I have a specific question concerning these star data for I think it's 27 and 39 GeV, which show when you look at the intermediate mass range and you fit a thermal spectrum to it, you find these rather large temperatures, which I found honestly very difficult to understand. And so that raises the first question, and that is whether there are any backgrounds that would potentially, explain these relatively large extended invariant mass tails, which for some reason have not been adequately subtracted. So do you have any thoughts on this? Of course, it could all be statistics and one just needs higher statistics data, but I wonder whether there might be some underlying physics that generates these apparent large temperatures.
Well, so what you're looking at here is the sources that we need to be aware of in this range are clearly sources that come from the charm contribution and Drell-Yan. However, they actually, and I don't have that plot here, they are rather low in their contribution and for 27 GeV. And so you're right that that's something you need to be very much aware of. I also will make the point indeed, and I think you already mentioned that we have to appreciate the uncertainties that are given on these measures. But yes, so you need to be very careful in the removal of charm and Drell-Yan, but that is done and is accounted for here and is accounted actually in the size of the uncertainty.
Okay. Thanks.
Yeah. No, you are the next.
Yeah. Hi, Frank. I actually have I have a question on the same page. You see on the left, you say average TIMR higher due to longer lifetime. I did not make the connection for higher temperature due to longer lifetime. Can you elaborate on that point? Yeah.
if the system lives longer, then and the radiation is dominated by the quark, the QQ bar radiation, then a longer system will, I mean, you'll see the average should then skew more to higher temperatures because the dominating radiation.
Why is that?
I mean, there is, in addition to your to the QGP contributions, there is a contribution from hadronic radiation. And so if your system lives longer and has a longer QGP lifetime, then that will increase the contributions, or, well, not increase contribution, but increase, if you look at the average lifetime, including of the QGP phase, that will
I see.
make your average larger.
I see.
Whereas for the hadron gas, your temperature would be somewhat lower. I mean, if you look at the right plot here, you may see this. If the lifetime was such that the radiation of the QGP would be less, then you can see that the hadron component, hadron gas component, may dominate and effectively lower your temperature, the average temperature. Sorry.
Okay. If I may, can I ask Ben a question related to this plot? Because I also heard this question, why stars dilepton temperature, the parameter is so high. What is the limit? I thought at RIC, top energy collisions, the initial temperature is about 400 MeV, is that right? So why, let's say we have 300 MeV, it's a big worry. Of course, we should be careful with the potential background contributions, but is there a physics limit from this plot, Ben? Do we know?
Well, this is not the top RIC energy, right? And so when you go down to, say, 27 GeV, it's very difficult to get the system to explain that the system actually ever heats up to that type of temperature.
And that the radiation is dominated by that high temperature and rather than by the much larger volume later.
Exactly, right? So, I mean, even if it were, it would be an extremely short moment. And it's very difficult to explain that. That's why it's important to really know whether this is, if this is true, then understanding the initial conditions in this energy range is something that theorists need to think much harder about.
Okay, thank you.
Okay, I think Rob has his hand up.
Yeah, thanks. Hi, Frank. Thanks for the nice overview. I wanted also to chime in on that discussion. And in fact, I fully share the concerns that average initial temperatures is still an average. It's not just the initial temperature, right? It's still somewhat of an average. That values of 300 or more at these relatively low energies are hard to imagine. But I think there are already some hints what even looking at this slide specifically what that could be. Let me first iterate one more thing for the NA60 temperature, which was quoted as 205. And that is actually consistent with what you get from the PT spectra, because the PT spectra also give you 200. And the PT spectra have an extra flow in it, and the flow is small, but it cannot be more than 200 in the PT spectra. So that value is actually consistent with the PT spectra or MT spectra that you mentioned later, with that 200 you mentioned later. So then the question is what's going on? And I think first clues are already here in the transparency. So you can increase the fit range from 2 to 2.5 GeV and you get already very much significantly higher temperature. So you look at the plot on the right-hand side. What's happening there is that you actually, you can speculate a little bit, and that's what I'm going to do. You start seeing actually power laws coming in there. It's not an exponential beyond 2 GeV, and and then of course also meaning of temperature is not all that meaningful anymore. But if you have such a sensitivity by just extending the fit range by half a GeV, it's already a bit fishy. But what I think is that there are actually power laws coming in from pre-equilibrium radiation, and that has been investigated by Sören Schlichting and collaborators for, I think, LHC energies, and they see it and it's there. The question then really is how far down in collision energy should it be there, but or how significant it is. I think there must be something between Drell-Yan and thermal radiation, and I think that's something that, in my opinion, is the most likely candidate for this enhancement that you see beyond 2 GeV. And if you do fits to 2.5, 3 GeV, you may pick them up, but you don't necessarily pick them up at if you limit your fit to 2 GeV, right, as NA6 did.
Yeah, that's a good point. The power laws are, so Drell-Yan and other primordial contributions are not following an exponential but a power law distribution, and you're absolutely right. They are kicking in sort of in this range. At least at the LHC, we know for sure we have to deal with it. It's still not completely clear to me how that at 27 GeV applies, but yeah, your point is very well taken. Yeah.
Okay, Zhao Chen, you have a comment, hands up.
Yeah, maybe this question is, I have a question to follow up with Rolf's comments. So we actually don't know where is the limit. Is 2 GeV or 2.1 or 2.2. So that is the difficulty. So how do we select actually a valid mass range to fit, right? So there is no hard cut from the experimental measured data. How do we know the boundary?
Well, if I can answer that. So, what was suggested indeed is that you will look at how well a exponential fit behaves. If you see that pushing it into a region where power laws are becoming more important, then you will see that actually affect your fit quality. So one way to look at this would be to really look at how well your fit is behaving as you push it to a range where power laws may become more relevant.
Yeah, maybe Rolf can, from the theoretical calculation, can also aid this.
Mm-hmm.
Give estimation, right? So, but the difficulty is still there, even though we fit when it close to the 2.5 to 3 GeV, in that region, we have a much lower production rate. The uncertainty there is not that good for us to actually fully constrain it's a power law or exponential shape, right? So, yeah. Okay, that is actually my comment.
Yeah.
Okay, Anthony.
Yeah, thanks for the nice talk, Frank. To this point, if I understand, at least from what we proposed in Alice 3, that the PT range that one chooses can affect how you sample earlier and later temperatures. So, for instance, if you have a higher PT cut on your electrons, in principle, you sample higher temperatures, and a lower PT cut samples lower temperatures. And it's just a humble suggestion, maybe for Star would be to it might be difficult with the statistics, but maybe investigate doing different PT cuts on this measurements to see what happens to the temperature itself.
Right.
Could be tricky, but
we're looking here at, so I mean, we know that there's in very mass spectrum for very low PT significant contributions that one needs to be wary of, but that I think in these calculations the PT cutoff is I wouldn't think it would be a concern, but I understand your point. Yes. Yeah.
Okay, any other questions or comments? If not, let's thank Frank again for this nice talk. I think we can close today's session here and let the control back to E.
Thank you so much. Thank you all. See you next time.
Thank you.
Thank you.
Thank you. Goodbye.
Bye.